Isoentropic efficiency of steady flow devices will be the focus of this lecture. In the previous lecture, we tried to derive the work expressions for a reversible steady flow system. We had earlier looked at the work interaction for a quasi-static process in the first part of the class, and then we had showed that it was of the form of PDV. As opposed to that, when you have a reversible steady flow system, we derive the expression of the form integral VD. Okay, so such system we are looking at goes from state 1, let's say, to state 2, and there is a work interaction. So when you state the work interaction is of the form VDP, we are looking at area under this curve. Okay, so this is the area that is of relevance. So we derive this expression, that which is the work input involved as we move this fluid from state 1 to state 2. So in many cases, the change in kinetic energy and change in potential energy is much less compared to this particular term. So these can be neglected. So we end up with just this term. Okay, so this is the work output, this is the work input expression. So this also points to the importance of specific volume in work interaction. So supposing you want to get maximum work out of the system, you want to keep the specific volume as high as possible. However, supposing we want to incorporate work into the system, you want to keep the specific volume as low as possible. So, for example, here we are looking at a compressor which increases the pressure of the fluid from P1 to P2. This will involve increase in temperatures and subsequently increase in specific volume. So if you operate the system isotropically, the work that is involved in this change will be the highest. The other limit is if you operate the system isothermally, that is, you are keeping the temperature constant by removing heat from the system. Because of that, the specific volume will decrease and you are able to save this much amount of work being incorporated into the system. In most cases, you are not in either of the extremes, you are somewhere in between. So this is what we saw in the last lecture. In this lecture, we would go towards a set of topics. Let's begin with this topic. For example, a set of topics involving isentropic flows. Let's also rationalize why we are involved with isentropic flows. So what is the objective here? Our objective is supposing a steady flow device goes from P1 T1 to P2. Okay, so we want to, and supposing in this case we are looking at a turbine, that is a work generating device. We want to ask the question, what is the maximum efficiency that is possible such that we keep the initial and some parts of the final state the same. Okay, so in this case, the initial state is P1, T1. The final state is characterized by P2. So we want to compare the efficiency of the actual process. Actual process is always irreversible, with the efficiency of an ideal process. Okay, so we would see why isentropic conditions are useful for characterizing the efficiency in some asymptote. So we had earlier looked at such similar questions. We had analyzed a Carnot cycle. Carnot cycle is in a way an abstract ideal cycle which gave the maximum work. And then we saw all kinds of irreversibilities decrease the amount of work that you can obtain. Okay, so this is an asymptote to reality. This is the real system. So in some ways, this is equivalent to, we will see this is equivalent to this system. So in most cases, what we see is that the condition that exists here, okay, for example, in the turbine, you keep the system adiabatic. There is no heat exchange between this control volume and the environment. Therefore, this gives us a clue to answer this question. How do we measure the efficiency of the actual flow device with some ideal device? So the ideal device has idealization at two levels. One is because it is adiabatic, it operates adiabatically. And also if we add an additional constraint that internally there is no irreversibility, then we can say that an isoentropic device operating reversibly would be your ideal system. Okay, so that is going to give the maximum efficiency, maximum work out of a turbine. And the other way around, we proved this in the last lecture. If you're, let's say, if a device requires work, okay, so you can, such a device is also going to require the minimum amount of work that needs to be incorporated to facilitate certain change in thermodynamic properties of a flow device. So we are emphasizing on adiabatic operation and reversible, internally being reversible. So that is why we are going to focus on isoentropic analysis of a series of devices that are of practical relevance in engineering systems. So we'll begin with an isoentropic efficiency of a turbine. So a turbine is a work generating device. So the actual turbine work will always be less than an work generated by an isoentropic turbine. So if you neglect potential energy and kinetic energy changes, we can do enthalpy balance also. So let us look at this in some detail. So what does a turbine do? So what turbine, for example, there is in this example, P1 T1 is 3 megapascal. Pressure goes from 3 megapascal to 50 kilopascal, and there is some temperature change. Okay, so what our initial state is having a pressure of P1, and we argued that the isoentropic condition is going to give you the maximum efficiency. So in this H versus S diagram, the Mollier diagram, we have a line at P2. This is the exit pressure. The exit pressure is the same for your actual system as well as for the ideal system. But what is different for an ideal system is the inlet entropy and the exit entropy is one and the same. Okay, so because of this reason, the work that you get from an ideal device, which is characterized by Ws, is more than the work that you can obtain from an actual device. Okay, so the real system is not isentropic. The entropy always increases. So you are in this curve and not along this line. So you are from enthalpy balance. The difference between enthalpy of this system minus this system is going to give me the work interaction. So that's the term here. And for the ideal system, the enthalpy difference can be the difference in enthalpy can be used for obtaining the maximum work that is possible in an ideal system. Okay, so again, for this system, we are representing the changes in a TS system. Okay, for the ideal system, there is no change in entropy. The real system has an increase in entropy. And note that the difference in temperature between the real system and the ideal system. This is the temperature for the real system, and this is the temperature for the ideal system. Okay, so you only keep pressure at the exit to be the same. You cannot keep both of them same, because the entropies of the ideal system is different from the entropy of the real system. All right. So this is a way to quantify the efficiency of a turbine. So typically the turbines operate about, large turbines operate about 90% efficiency, and small turbines have lesser efficiency. So this is fairly significant. Okay, so the overall the efficiency of a turbine is significant, but turbine is just one part of a power plant. Okay, so if you look at the efficiency of a typical thermal power plant, it will be about 40%, but turbine operates at about 90% efficiency. Next, we move on to a device that requires work to be incorporated into the fluid stream. So that's a compressor or a pump. A compressor operates on a vapor. A pump operates on a liquid. For example, here we have an air compressor that increases the pressure. Okay, so for the real and the ideal system, inlet P1 and T1 are one and the same, but for the real and ideal system, P2 is the same, but temperatures can be different. For the ideal system, the minimum work that needs to be incorporated is under isoentropic condition. Okay, so that again, neglecting the kinetic energy and potential energy changes, the work can be obtained from difference in enthalpy. Okay, so the actual compressor work, this is greater than the minimal work that needs to be incorporated into the fluid stream. The minimal work is obtained from difference in enthalpy in the following manner. Okay, so the enthalpy of the ideal stream is obtained by enforcing the isentropic condition. This is the enthalpy of the ideal system. Okay, so but in a real system, that does the ideal system operates along this line under isentropic condition. But in a real system, the entropy increases, because of which, but the pressure P2 is just the same. Therefore, in the Mollier diagram, you would see that the enthalpy is different. Okay, so all right. So enthalpy is higher in this case. So the actual work in the real system is greater. For a pump, because it operates on a liquid assumed to be incompressible, we have a simpler expression. The specific volume is not changing. Therefore, we saw this in the previous lecture too. The actual isentropic compressor work in an actual system is still given by difference in enthalpy. Okay, assuming that the changes in potential energy and kinetic energy can be neglected. So you can equate the actual work to enthalpy difference, enthalpy of the inlet stream minus the enthalpy of the outlet stream. However, to obtain the isoentropic compressor work, we have a simple expression which we saw in the last lecture. specific volumes times difference in pressure, because the specific volume does not change. The integral can be um, computed in the following manner. So the typical efficiency of a compressor is about 95%, which is also high. As you can see, even though each of these components act at reasonably high efficiency, the entire power plant doesn't operate at this efficiency. It's about 40 to 50% efficiency. So because of the importance of specific volume, we saw in the last lecture too why you need to keep the specific volume less if you want to incorporate less work. Okay, so it's the other limit. The other limit of work generating device, like for example in a turbine, you want to keep the specific volume high. However, for a work in the system wherein work is incorporated, you want to keep the specific volume less. Therefore, you artificially cool the system. Like for example, if you have a compressor, an air compressor, you would the act of compression is going to increase the temperature, thereby increasing the specific volume. You don't want this to happen because you want to have lesser work incorporated into the system. The work input should be less. Therefore, you artificially cool the system. Okay, you realistically cool the system. Therefore, the entire notion of isoentropic analysis is not valid because you're no longer operating the system adiabatically, right? So that's just isoentropic analysis doesn't give you a limit to compare the efficiency of a real device with some ideal device. Okay, so the adiabatic expression is no longer valid. Therefore, what you compare is a work expression that is obtained from isothermal efficiency. Okay, so if you operate this device isothermally, your specific volume is as less as it can be. For a given change in pressure, P1 to P2, you can keep the specific volume the least if you operate the device isothermally. Okay, so that gives you a limit in your work. Okay, so that is the least work that needs to be input into the system, and the actual work is this one. Okay, so the efficiency of such a compressor operated with a cooling system can be calibrated with this efficiency measure. Then we move on to another flow device, which is a nozzle. Nozzle, in this case, is typically used for increasing the kinetic energy. So a measure of efficiency of nozzle is for, let's say you have the same input condition, that is the kinetic energy or the temperature, pressure, and the kinetic energy of the input stream is the same between the real device as well as in the ideal system, which is an isentropic nozzle. However, the real device has a different kinetic energy, lesser kinetic energy compared to an a nozzle operated isotropically. So the difference between kinetic energy or the ratio between kinetic energy is a measure of efficiency of a nozzle. Again, here, of course, the kinetic energy differences play an important role. Therefore, the balances, enthalpy balances, will include a difference in kinetic energies. So this is the inlet stream. Kinetic enthalpy is this one. The outlet stream enthalpy is this, plus there is a kinetic energy term. All right. So the difference in, because for the real device as well as in the actual device, H1 is one and the same. So this is one and the same for a real device as well as the idealized device. For idealized device, it operates isentropically. Therefore, in the Mollier diagram, what you get is the enthalpy of the outlet stream is lower. That means the difference between this and this is the kinetic energy that is gain of your flowing system. This kinetic energy gain is greater because your exit enthalpy is lower. Okay, so in the Mollier diagram. So, but for actual device doesn't operate along this line, but operates along this curve. Your enthalpy is greater for your actual device. Because of this, the kinetic energy gain in an actual device is also lesser compared to kinetic energy gain in a real device. Again, the nozzles are also high efficiency devices which can operate at around 90% efficiency. So in the having completed entropy calculations and analysis of a range of devices where irreversibilities play a significant role, as a final topic, we will look at entropy balance and aspects of entropy generation. Okay, before we move on to the last segment of second law analysis, which is exergy analysis or availability analysis, that we will see after completing entropy balance and entropy generation in the next lecture. Thank you.